Okay, so now we can talk about mode of operation. So there will be some notation, but generally we will, instead of using the mathematical notation, we will talk more on the pictures. But these are some abbreviations. One of the important things is IV stands for initialization vector. And sometimes we are going to use nonce. I will explain them in a minute. And generally, K represents the key, N is the total number of blocks. Sometimes I use MI, sometimes I use PI to represent plaintext blocks, but most of them are easy to guess. Okay, so let me give a brief explanation to what is an initialization vector and what is a nonce. Initialization vector IV is an input to a cryptographic algorithm or primitive like block ciphers, hash functions, message authentication codes, etc. Cryptographic nonce is an arbitrary number that may only be used once. That is the main difference. IV is generally fixed. For instance, for hash function or a block cipher mode of operation, IV is fixed in the standard and everybody uses the same IV. Okay, but for nonce, you have to also randomly generate it, but you cannot use it twice. Okay, if you use it twice, then the security is broken. This is why it is important. Nonces and IVs should be generated randomly, and this is also a problem sometimes in the literature, especially for stream ciphers. Instead of the word nonce, some people use initialization vectors, and there using the same IV causes a problem. But I will call it a nonce instead of IV. Okay, so there's a little bit confusion in the literature, but still, for me, nonce is the thing that I can only use once. And IV is fixed and known by everybody. Okay. So there's a NIST documentation from 2001, which is NIST 800-38A, and it suggests the following modes of operation, like ECB, as we mentioned, CBC, CFB, cipher feedback, output feedback, and counter mode. And in the addition to that document, they added in 2010 XTS, which is the standard IEEE standard for full disk encryption. So this is also confusing because this NIST document starts with ECB, and everybody for this reason thinks that ECB is secure. So NIST also kind of apologized for this, and I will show a slide at the end. They are going to modify this document, especially it is under development right now. So in the future, they will make absolutely clear that you shouldn't be using ECB, okay? And the documentation will be better. So if there are, and these are the modes of operation listed in this document. So you can find other documents with different modes of operations. So the question is which one to choose, okay? Which one is secure or which one is fast? So the choice of the mode of operation affects the security, but also the performance, okay? So electronic codebook, here each message block is encrypted with the secret key. But instead of this, let's look at the pictures. So we already mentioned this. The input is divided into blocks, and they are encrypted independently, right? So for the person who wants to decrypt, they receive the ciphertext blocks. So they decrypt back with the same secret key and obtain the plaintext blocks. So you might think that this picture is obvious, but I am deliberately showing it because here the encryption and decryption are shown in different colors. In some of the operations, mode of operations in the future, you will realize that after some point on, the person who wants to decrypt still will be using the encryption operation, but not the decryption operation, which is the inverse of the encryption, okay? Because some modes of operation will turn a block cipher into a stream cipher, which we haven't discussed yet. But when you turn it into a stream cipher, then the encryption and decryption actually works in the same direction, okay? So this is why be careful about the wording here, enc and dec, but also the colors, okay? So the ECB actually has a lot of advantages because it is parallelizable. A block can be encrypted without waiting the encryption of other blocks. It has random access. A block can be decrypted without waiting the decryption of other blocks. Error propagation is limited to a block. This means that if a single bit of block is flipped due to a transmission error, it does not affect other blocks because you are doing everything independently, okay? This is why you have parallelizability, why you have random access, etc. But the problem is identical plaintext blocks are encrypted to identical ciphertext blocks, so this is unacceptable. So this is why you cannot use it in the practice. But another thing is that this doesn't provide self-synchronization. This means that if some ciphertext bits are dropped, this synchronization cannot be achieved. Let me make it clear like this. Assume that this is the ciphertext I sent you, but first bit of C1 is dropped. Okay, so everything shifted one bit to the left. At this point, if you try to decrypt, then from this point on, everything will look like garbage. So you don't actually have any self-synchronization, but this means that you don't actually have any authentication. But here, the authentication I mean as data authentication. This is why you need authenticated encryption or message authentication codes, okay? So all of the modes of operation I'm going to show today actually will not have self-synchronization, okay? This will be more clear when we talk about authenticated encryption. Okay, so let's move on to Cipher blockchaining mode. Here is the picture for it. So everything is now serially connected to each other, and you start with an IV. In the decryption part, you simply flip the picture. So it becomes like this, okay? So error propagation is limited to 2 blocks. Fixes the security problem of ECB mode. Parallelizable decryption, but not encryption. This is important because, as I told you before, if I want to encrypt P2, I need to wait for the encryption of P1, and this has to wait for the encryption of P0. But when decrypting, you don't need to do that, because if you want to decrypt C2, you can decrypt and come here. And for the XOR operation, you already have C1 and you can XOR it. So this actually allows you parallelizable decryption, although you don't have parallelizable encryption, okay? So non-parallelizable encryption, no random access. And here is a problem. If Ci and Cj are equal, this means that, for instance, C2 and C1 might be identical, or some distant ciphertext blocks might be identical. But this means that then the previous ciphertext XORs will give you XOR of Mi, XOR Mj. Due to birthday paradox, such a case happens with the square root of 2 to the B blocks. So if B is really small, this happens a lot. For instance, think about B equal to 32 bits. And when you encrypt 2 to the 16 blocks, which is just 65,000, then you will observe this. So it is not secure. So this is why you need to choose your block size large, like 128, so that this chance reduced to 2 to the 64. Here you might assume that you will never encrypt 2 to the 64 blocks. As a single person, yes. But if you have a cloud service and if your company uses it, you will be using the same secret key for encryption of huge amount of data, and this might happen, okay? For this kind of different problems, actually, cloud servers asking for AES to be modified to support 256-bit block size. And currently, a standardization process is going on. Okay, so let me move on to CFB. In the CFB, as you can see now, the picture is a little bit different because I'm not encrypting P0 like here. Instead, I encrypt the IV, then I XOR the result with P0. Okay, then I take C0 as the input of the encryption, like this. So as you can see here, after the encryption, here I'm producing some values, which we will call key stream when we talk about stream ciphers. Then I simply XOR it with the plain text to obtain ciphertext. This is important because when you do the decryption, the picture is almost identical. As you can see now, the person who decrypts also performs the encryption operation, but instead of XORing this output value with P0 to obtain C0, they use this output value to XOR it with C0 to obtain P0. So you simply swap the places of PIs and CIs. So encryption becomes identical to decryption. Okay? This is good if you want to implement it on hardware, because now you don't need to deal with the decryption. Okay? So it has some advantages. Error propagation is limited to 2 blocks, but non-parallelizable, no random access. A little bit modified version of this. So you might think that this is exactly the same as the previous one, but the only difference is that in the previous one, this line was here, okay, after the XOR operation, but now it is before. So the inverse of the picture is also PIs and CIs swap places. So this way, this actually gives you the following advantage. You can do the encryption before even the plain text is ready. You can obtain these values and keep it in the memory. And when the plain text comes, you can simply XOR it and give the ciphertext as the output. Okay? In some communication devices, this is what is preferred. Okay. Yes, encryption does not depend on previous ciphertext, etc. But we want something better. Let me move on to counter mode of operation, then I will explain why I like this more. Here, in the counter mode of operation, generally what you do is as follows. You choose a counter, assume that it is 0. You simply encrypt 0, and then XOR it with the plain text. Then you increment your counter, make it 1. You increment it to 2, etc. Now, as you can see, there are no lines connecting to this picture. So the encryption is almost identical. You change the places of the CIs and PIs. But now you have parallelization, random access, error propagation is limited to a block, encryption does not depend on previous ciphertext. So this is like the best you can have. So it provides you every solution. But here the problem is that you shouldn't be allowed to use the same counter to encrypt 2 different plain text. Okay? This causes a problem. And this is important because not much people knew it. And this has happened when there was a ransomware attack around 2010. So the initial Turkish version of the famous ransomware called Cryptology uses AES in counter mode of operation. And they simply encrypt your 2 megabytes of your files. So your files becomes unreadable. Then they give a message saying that you have to now pay money so that they can decrypt them back. At the time, they asked for 2 Bitcoins, and it was amount to $200 at the time. Think about all of the money they gathered around that time. Nowadays, when you receive such an attack, you are asked to pay 0.001 Bitcoins or something. Okay. However, the Turkish version uses the same counter for every file encryption. Now this is a good thing because obtaining one unencrypted file allows us to decrypt every file since XOR of the plaintext and the ciphertext provides the key stream. So let me explain it like this. Assume that they are using the same counter all the time. So in your computer, you have the ciphertext of a file, right? Because there it is encrypted. But maybe that is a file, you already know. In our case, this happened to a professor here in our university. I obtained a PDF file on his desktop, and it was actually a paper he published at Elsevier. So I went to Elsevier and downloaded the same file. So this way I obtained the PIs. So I simply XORed them and obtained these output values. Now that I know them, now I can always use them and XOR it with other ciphertext values to obtain the plaintext. So I recovered all of the files. Okay, this is how you can use a good mode of operation in a bad way. Okay, just because of this, a lot of people think that counter mode of operation is insecure and never to be used. Actually, this is the thing you should be using. Okay, so actually, authenticated encrypted version of this is called GCM, and almost everything uses this. Zoom uses this. Your Android or iPhone devices, actually, whenever you take a picture or any file you record on the device, actually they use this mode of operation to encrypt it in the device, because they come with full disk encryption. Okay, so in order not to use the same counter all the time, you cannot easily keep a list of all of the counters you use. What people generally do is as follows. For instance, if you're using AES, this is 128-bit block. So you randomly generate the first 64 bits, which I call nonce. Then you use the counter 0, 1, 2, etc. And whenever next time you want to encrypt something, you randomly regenerate a nonce, which will be different than the previous one. So you, again, can use the counter as 0 because the first part of the block is different. Okay, so this is the good thing. So this is actually what you would prefer to use, okay? So the last thing I didn't mention is the XTS. I would not go much into detail, but this stands for XOR Encrypt XOR based tweak codebook mode with ciphertext stealing. So very strange way of abbreviation. AES with XTS mode is a disk encryption standard since 2007 as IEEE P1619. For messages with length not divisible by B, the last 2 blocks are treated specially, and the general picture is something like this. So you apply some operations as counters here, then you encrypt them. So I'm not going into much detail, but if you're interested, you can find this details. Okay. So for further read, you can look at this standardization document of NIST, but Philip Rajaway actually wrote a very nice, more than 100-page, freely available PDF, which you can download, and you can see many different modes of operation, which are them are secure, which are them are bad, and a very nice documentation about it. Okay, so let me go back to our motivation. So I said that this was if this is our BMP file, if I encrypt it, it becomes this, which is no good in the ECB mode. Question is, what happens if I use the counter mode? So as you can see, there are no visible patterns here. This is what a real encryption should look like. So let me go back, original ECB counter. Okay, same applies for our different logo here and this. Okay, so let me finish with two recent developments. So NIST around 2023 said that they decided to revise this document, and the most important modifications will be as follows: limit the approval of ECB mode to instances that are specifically allowed by other NIST standards or guidance, such as the challenge response protocol here. Clarify the requirements on the initialization vectors and the counter blocks. Provide guidance on the importance of incorporating authentication where feasible. Incorporate the content of the addendum, the 3 variations of ciphertext stillings for CBC mode, into the revision of this. And also improve the editorial quality and update the references. This is important because some of the standards, especially if they're 20 years old, when you read it, you wouldn't understand what they're saying. Just go to this document and you won't be able to implement it just by reading that document. You wouldn't understand which bit goes to which. So this is why it is always good idea to update more than 20-year-old documents. Okay. And the final example, I will finish it. So when I was teaching last year, there was a nice paper on ePrint. I think it is not published, so you can look at the full document, but it is about breaking XCB. This is an IEEE standard for encryption of sector-oriented storage media, and it comes with a proof of security for block-aligned input messages. So assume that then there's an IEEE standard and it claims that there is a proof of security, but the academicians break it very easily, just using just a few, similar ciphertext and they direct it. So you can see here, let me read it shortly. So our proposed attack is a plaintext recovery attack under a chosen ciphertext attack model. For an M-bit ciphertext, the attack recovers the first M-N bits of the corresponding plaintext. Here, M can be quite large, such as sector sizes, typically used in disk encryption, like 512 bytes or 4 kilobytes. And N represents the block size of the encryption primitive, like 16 bytes. So think about it, M-N is like 4 kilobytes minus 16 bytes. So you capture that part. So consequently, the attack is capable of recovering almost the entire sector. And in a paragraph, they here briefly explain it, but of course you can read the full paper to see how they do it. So this is important because when somebody makes something a standard without asking the crypto people, generally that standard can be easily broken. Okay, so this is the main takeaway from here. Okay, I stopped the recording again. Now I